By the way, exams I don't have today. I will probably have them tomorrow. So the lab's pretty short tomorrow, so we should be able to go through it. Where was I? Oh yeah. All right. So this one, you'll see a lot of problems of this type in this chapter. It's kind of the classic ideal gas law chemistry question because it also deals with quantities. And we've already done all that stuff with the quantities, so it fits in nicely and kind of keeps it all building on each other. So in this case, you're given a gas, a pressure, a temperature, and a volume. So you can find number of moles using the ideal gas law. So we're looking for number of moles. That's going to be PV over RT. You don't need to like memorize these formulas. Well, you should know the ideal gas law, but you should be able to derive the next one just by algebra, right? Dividing both sides by RT. So if we plug those in, we're going to have to do a couple unit conversions here based on which R value we need. So since the R value that we tend to just know is the one that's in liter atmospheres per mole Kelvin, that means we need atmospheres for pressure. We need Kelvin for temperature instead of Celsius. So, oh wait, that's part B. Yeah, that's what we're doing, right? No, we're doing part A, sorry. So we got millimeters of mercury, so 250 millimeters of mercury. Yep, what? Oh, this is mine. You should be able to, I think I gave her one, yeah, thanks. Okay, and we should remember that there's exactly 760 millimeters of mercury in one atmosphere. So that tells us that this is .329 atmospheres. And then 20 degrees Celsius plus 273 is going to be 293 K. So all that put together, we can plug into the ideal gas law and get moles of ClF3. So pressure, 0.329 atmospheres. Volume, 2.5 liters, that's given in the question. R, we know, 0.0821. And sorry, this is getting small. Let's write it bigger. And then our temperature, 293 K. A little bigger over here. So I can evaluate that, 0.329 times 2.5 divided by 0.0821 divided by 293. And get 0.034 moles of ClF3. Is that what you got? Been wrong. All right, great. All right, but that's not the end of the question, because the question is how many grams of nickel oxide, nickel 2 oxide, will react with the chlorine trifluoride gas. So to do that, that's just a typical chapter 4 question like you would have seen on the exam yesterday or in the homework. So we're going to start with that quantity of moles. And go from moles of this one to moles of the other one. And then moles of that one to grams of that one. And that will give us our answer. So the molar mass of nickel oxide, what is it? I can't see that far. 58.7 and 16, right? 58 and 16 is 74. So that's 74.7. Okay. And the equation tells us there's 6 of these for 4 of these. Get those numbers right from the equation. All right, so I can evaluate that, 0.034 times 6 divided by 4 times 74.7. And 2 significant figures, 3.8 grams nickel oxide needed in this reaction. So that's how we deal with stoichiometry in gases, because it's difficult to weigh gases. So we often use pressure and volume and temperature to determine how much we have, and then do the adjustments that way. All right, good so far? Okay. The next part, we're going to look at what happens when this reaction is completely consumed. So assuming we have enough nickel oxide, what are the partial pressures of chlorine and oxygen? So we didn't talk about that term partial pressures on last week. Anybody have an idea of what that is going to be about? What does it mean to have a partial pressure? Yeah.
Pressure of each element.
Yeah, so like, does everybody remember how we defined pressure in terms of gases? Like what causes the pressure in a container when there's a gas in a container? Good? I think you sort of got it. Yeah. Go ahead.
It was like the force on the inside of the container.
Yeah, the gas molecules hitting the walls of the container. So if you have two different gases in the same container, would you expect that that would be a different pressure from individually? In other words, so you have one gas in a container and it's hitting the walls at a particular pressure. You have another gas in another container hitting the walls at a certain pressure. You put that together, do you expect something different to happen, or do you think the gases will still have exert the same types of pressures on the walls? What do you think? Why something different? They're going to hit each other too. Is that going to change the individual pressures that they exert on the walls? Maybe. So the answer is it doesn't actually. Let's flip over to our notes from yesterday or from last week. Okay, so let's say we have two containers. Inside container one, so let's, what was our problem here? Okay, so there's chlorine and oxygen. Those are the gaseous products here. So let's say we have a container with chlorine gas in it. And another container with oxygen gas in it. Let's say there's, some whatever number of chlorine molecules, some whatever number of oxygen molecules. And let's say that the pressure inside this container is 2 atmospheres. And let's say the pressure inside the oxygen container is 3 atmospheres. So assuming that temperature and volume are the same, that those are the same size containers and temperature is the same, there's more pressure in the oxygen one, which incidentally tells us which one has more gas in it, assuming temperature and volume are the same. Oxygen, because the higher pressure means more gas. So when everything else is kept the same, we can use pressure as a way to measure how much gas is there. Okay, so now let's say we put both of these into the same box. Same size box again. Now we've got chlorine and oxygen. What's the total pressure of this new mixed box, assuming everything else stays the same, volume, temperature? What's the total pressure of the new box? Somebody take a guess. What might it be?
Is it 5 or 3?
It's 5. Remember, pressure is proportional to number of moles, assuming everything else is the same. So if you take all the gas that was creating 2 atmospheres on the left, and all the oxygen that was creating 3 atmospheres on the right, and you put them all together, you have the same quantity of gas. It's all just in the same different container now. Well, it's all in the same container now. So now it's adding up to make 5 atmospheres total. So pressures are additive like that. And in fact, if we call this the total pressure, we can express that total pressure as a sum of the partial pressures. We call this the partial pressure of oxygen. This is the partial pressure of chlorine. So that's actually pretty easy. We don't have to worry about any kind of weird effects going on until we start talking about deviations from ideality, but that's different. We can just assume that if we have this much pressure of this gas, this much pressure of this gas, we put them together, it's just additive. And indeed, the individual proportions kind of stay the same. This is called Dalton's law of partial pressures. I don't know if it's important. I don't think it's important to know that term necessarily, but that's the point is important, that you can just add up the pressures and have the total pressure. Okay, so why is that important? Well, let's go back to the problem that we were talking about so we can see where that comes in. In part B, we're going to say is if it's completely consumed, what are the partial pressures of each of those at in the same flask at the same temperature? And then what's the total pressure in the flask? So how do you think we're going to be able to figure that out? Let's just look at one of them for now. Let's just take chlorine. So if you didn't know anything about partial pressures, if you didn't know anything about this stuff, you just knew the stuff from the last chapter, how would you solve this problem? How would you figure out how much chlorine you were going to get? What kind of quantities are you using for that? We've already solved in part A the moles of ClF3, 0.034 moles. So how can we figure out how much chlorine we're going to form in the product? Yeah, exactly. We would do a mole ratio, right? So let's do that. All right, we already did this part, so I'm just going to delete this. Actually, no, we'll probably need those numbers. Let's leave that there. We don't need these anymore. Try to write a little bigger this time. Yeah, so let's look at just how much chlorine we would make. If we want to know how much chlorine we would make, the theoretical yield, which we've done a bunch of times, you did on the exam yesterday. It's in the lab report for tomorrow, which we'll talk about a little bit later. I know there's some questions on that. We would say 0.034 moles of ClF3 times some quantity that would get us from moles of ClF3 to moles of Cl2. We'd go back up to the equation, look for those numbers. That's a 4:2 ratio. So we just cut that number in half and get 0.017 moles of Cl2. So that's easy enough. We've done that before. But the question is asking us for the partial pressure of chlorine. So can we get a pressure from what we have? Why not?
It's just I forget what you need more. Need more something.
Do you? What equation do we use to solve for pressure of a gas?
Oh.
Ideal gas law.
The ideal gas law. So what do we need for the ideal gas law? If we're going to solve for pressure, we need volume, moles, the gas constant, and the temperature. Do we have those things?
Yeah.
We do, because we can use that new number, 0.017, as the moles. So we can just solve the ideal gas law for chlorine and get the pressure of chlorine. So the partial pressure of chlorine, which sounds like some sort of fancy new quantity that we've never heard of before, is just solving for regular old pressure, but you're only using the moles of one gas if there's a mixture of a bunch of gases. So the pressure, PV equals nRT, so pressure is going to be nRT over V, if we do our algebra. And I'm just going to put a little Cl2 under that N to show us that we're only going to use the moles of Cl2. And if we just use the moles of Cl2, we just solve this the regular old gas law way, and we should get our partial pressure for chlorine. So 0.034 moles of ClF3 times R times temperature, which we've already done those conversions. Yes, thank you. I am using the wrong moles. All divided by the volume, which has stayed the same because we're in the same container, 2.5 liters. So that's our partial pressure of chlorine. So think about what we did there, because I think this is the biggest problem with partial pressure, is everybody wants to overthink it. Like, oh, it's partial pressure, it's this new thing, it's some special gas thing. It's not. It just is telling us that we don't have to do anything special. We can just treat the gases individually, and the fact that they're mixed in a container doesn't mean anything. They're still doing their own thing. They're colliding with the walls in the same way. The other gas is colliding in the walls in its way. Whatever, they're just mixed. They're not affecting each other in a way that we have to account for. So we can do the same thing for the other one, which is oxygen. But we'll solve for the partial pressure of oxygen using moles of oxygen. To do that, we have to do another calculation here. Okay. Just copy it over here. Get rid of that. I'm copying, and I know it's more annoying for you when I copy and paste because you have to write, but I'm just doing it to show you that it's the same calculation. Instead of chlorine, we're going to do oxygen. And if we go back up to that equation, I think that's 3 instead of 2. Yeah. .026 moles of oxygen. And then we do that same equation. So our partial pressure of oxygen is going to be the moles of oxygen times RT over V. Exact same equation, just now we're going to use a different mole quantity. Wait, what is it wrong here? Oh, did I do something wrong up on the previous one? off by 10 here, sorry. So now the new one should be 0.026 0.25. Our pressure of chlorine is 0.16. Our pressure of oxygen is 0.25. So then the last part is, what is the total pressure in the flask? What's the total pressure in the flask? How do we find that? Yeah, you just add them up. The partial pressures add to the total pressure. So the total pressure is the two pressures added up. All right, so we go back up to the equation here. Why, oops. Uh-oh. Okay. What did I do? Oh, somehow I put it down here. Okay. Why did we just ignore that nickel 2 fluoride? Why did we only bother solving for chlorine and oxygen?
It's a solid.
Yeah, only gases have pressures in containers. So even though it's there, we don't worry about it. And that's actually a really common mistake that I've seen on exams with these types of problems, where you're doing some reaction and then you're trying to find the partial pressures of the products. There's a homework problem like this too in the chapter 5 homework, where like you want to just solve for all of them, and then it doesn't work out, and the reason is because one of them is a solid. So you should ignore that one. That's not part of the pressure in the container. That nickel 2 fluoride is not contributing to the pressure in the container, so it doesn't have a partial pressure and it doesn't get added into the total pressure. All right. So did I like skip something, or it's just on two different? Oh, it's just on two different pages. Okay, well, whatever. We'll get to that stuff in a second. All right. So why this is this final result? If you think about what we did, kind of gives us a little bit of a shortcut if this comes up in other ways. Notice that, and I don't know if you noticed this, but it was kind of tedious to go through this because we're basically doing the same thing twice. So what would happen if instead we didn't want to do all that stuff twice? Does anybody see kind of a shortcut or another way that we could think about this? Yeah.
Take the total volume of the container.
No, I think you're on the right track. Yeah. So like the two gases are in the same container. They have the same volume. They have the same temperature. So the only thing that's different about them is their partial pressures, which is dependent on their moles. So if we know the moles, we can always figure out what the partial pressures are going to be. Let me show you how that works. Example here. Another example. I just assumed this one would be good enough. So let's jump back over to here. So we've got our partial pressures. I guess they don't have that in this part of the book. That's okay. We can talk about, if we talk about the same example here, because these numbers are nice and easy here, we can also think about this as the total pressure in terms of something called the mole fraction. I'll keep my color scheme here. Explain what this is. Mole fraction is just like a percentage. So in this particular mixture, we can figure this out actually. What is the mole fraction of chlorine? In other words, what percent of the total mixture is chlorine? Yes, right. I flipped the numbers around in my head. Yeah, 40%. How'd you get that?
Because it's 2 over 5.
Right. So you've got two atmospheres of chlorine divided by 5 atmospheres total. So chlorine accounts for 40% of the gas mixture, or its mole fraction is 0.4, is another way of saying that, because a percent can be a fraction and vice versa. And so you can actually solve for these various pressure, partial pressure things just by knowing the percentages of each of them. All right, let's jump back to this other problem, and I'll show you another way that this can be asked. So I'm going to copy this part of it. Again, we can put it back in the notes here. And let me show you the other way that this problem is sometimes asked. So here's our equation again. And what did we figure out the total pressure was? It was 0.41 atm. So what if I just told you that? So how can we solve for the partial pressures of each of those, given the total pressure, without doing any ideal gas law stuff? We could do this problem even if nobody told us anything about the volume and the pressure. Well, we couldn't do the stoichiometry part, but we could do the last part. How can we figure out the partial pressure of each gas without using the ideal gas law, based on what we were just talking about? Yeah.
P total equals, and you do the mole fraction.
Yeah, how can we find the mole fraction?
In the equation.
Yeah, exactly. It's in the equation. So it's 2 chlorine for 3 oxygen. That's what the equation tells us, right? So that means that the mole fraction of chlorine is 2 over 3, or 33%, or 67%. Sorry, not 2 over 3, 2 over 5, or 40%. And the mole fraction of oxygen is 3 over 5, or 60%. So we can solve the mole fraction just by adding up the total moles of gas and then looking at each one. And if we calculate this out, 0.4 times 0.41, so our partial pressure of chlorine is 2/5 times the total pressure, or about 0.16. And our partial pressure of oxygen is 3/5 times the total, or 0.6 times 0.41. So we can figure out the partial pressures just by looking at the mole ratios, if we're given the total pressure. All right. Questions about that one? We'll practice these a little bit more. Let's take a look at some of these others before we go on to some new concepts. So these two figures here, I can't quite get them both. There we go. They both have the same question. No, they don't have different questions, but you can use the axes to figure that out. So the top one is the relationship between volume and pressure, and the bottom one is the relationship between volume and temperature. Talk with the person next to you or the other people at your table and decide which curve you think best fits that that idea.
16?
Both of them.
The first one is.
The first one's, it's the same question. The first one's volume versus pressure, and the second one's volume versus temperature. So it should be on your sheets as well that you have there. You can put them between you and take a look at them. So decide which one best. I've got some markings on there that I couldn't erase, but just talk about which one you think fits best for each relationship. And how you know. You can use language like, as this does this, this should do this. And, but like use the real actual words.
When it means by volume, it's volume of the container, correct?
Yes, right, volume of the container, volume of gas. And it's assuming that it can change. So like a plunger type situation or something like that.
Okay. Yeah.
All right, everybody feel good about this one? So what do you think about for the first one, the relationship between volume and pressure? Maybe I go with A. Place. Okay, B, C, D, E, All right, so we're a little scattered around here. So let's talk about this. Okay, let's imagine our plunger again from what we talked about last week. We've got a plunger. You increase the pressure on something. What happens to the volume? If I've got a plunger with some gas in there, and I increase the pressure, what happens to the volume? We go up or down? Down? Everybody see that? If you increase the pressure, you can think about squeezing a balloon too. If you increase the pressure on the sample, the volume goes down. So let's look at those lines here and think about which one, as pressure goes up, volume goes down. So which ones, and there's a bunch of them here, but which ones fit that description? What? A and E. The other three are going the wrong direction. The other three are showing as pressure goes up, volume also goes up. So that's the opposite trend. Between A and E, they're both showing the same trend, the trend in the same direction at least. That as you increase pressure, the volume goes down, it's smaller. All right, so how do we decide between A and E?
Well, based on its relationship, which is linear, you can't go with A because that's exponential.
Well, careful about that. E is not actually exponential, E is hyperbolic. Right. So let's think about like what would happen long term. Let's look at limits. Anybody like calculus fans? Yeah.
I do it about fun.
All right. So what does it mean when we talk about limits?
As long as
Everyone cries and throws up a little bit.
as this thing approaches a certain number, like what does this number approach to?
Yeah, just like we're going to talk about infinite limits. So what happens if you just keep increasing the pressure? So let's look at our plunger again. All right. Let's say that we are increasing the pressure, and then we keep pushing, and we keep pushing, and we put a car on top of it, we put 3 cars on top of it, and we put whatever, and we keep increasing the pressure. What happens long term to that? If we could put infinite pressure on there, what would the volume become? But close to zero, maybe not quite zero, but depending on the pressure, yeah, because we'd have to actually force the air out of the container to get to zero. But as you increase the pressure, you're getting closer and closer to having no volume at all. Could you go negative? Could you create negative volume in the syringe? You couldn't. So does that help us make that distinction? Yeah, because why? Yeah, as A continues, it will eventually cross the x-axis and become negative. So A is telling us that as we increase the pressure on that syringe, eventually we're going to create negative volume. And that doesn't really make sense. It's going to approach zero. And then the same thing in the other direction. As we increase the volume of the container, the pressure is going to get smaller and smaller and smaller and smaller because now you've got the same amount of gas in a much larger container. But it's never actually going to get negative. There's no such thing as negative pressure in this type of a situation. So E makes the most sense on that one. Both A and E show the correct trend, but when we think about what would happen as these continue, that's where we can make the distinction. Okay, what about the next one down? Now we're talking about volume and temperature. So does anybody want to just describe the trend between volume and temperature? What happens as you change ones? Let's use a sentence like, if you increase blank, you blank blank. Anyone? Go ahead. As volume increases, temperature increases. Or another way to think about that is as you increase the temperature, as you heat something up, it expands. Heat up the gas, it expands. Volume goes up. So which lines represent the trend going in the correct direction? B and C, and D is also going in the correct direction. So which one is correct, or how do we make that decision? Is it B, C, or D? What do you think? You go C? Why C? You're right, but why?
I don't know.
Anybody want to give a reason now that I've said that it's right? Yeah, Eric.
You have like no temperature, just like D0 in like the equation, right?
Right. So according to this trend, if you were at absolute zero, if you had no temperature, then you would have no volume. Now we know that's not quite true because atoms take up space. But what that's really saying is we know that a gas, most of the space in a gas is space. Only a little bit is actually atoms moving around. If those atoms stop moving, then that space no longer exists, so you're effectively at zero volume. The important thing is there isn't some like volume that we start at there. And then, so that's why B isn't right. And then D doesn't work because as temperature increases, it doesn't suddenly start shooting up in volume without increasing the temperature. It retains its linearity. And that one, we can look at the equation also. If you remember it, V over T is constant. So another way of looking at that is V equals constant times T, which is the equation of a line with no y-intercept. So C makes the most sense there. Any questions about that one? All right, so here are some basic like ideal gas practice problems. We're not going to go through those right now. We'll have hopefully have some time to practice. I want to look at another thing that we can do with partial pressures, which is this problem right here. I'll show you why. Why we have to take partial pressures into account, an equation that it doesn't necessarily tell us that that's the case. So here's a real thing that we would do. We haven't really talked about this, but collecting gases in the lab is itself a little bit of a challenge. So let's say you are doing a reaction that produces gas, and you want to track that gas and measure how much you have. How would you do it? Do you have an idea? So you're doing a chemical reaction, it produces a gas. How do you capture the gas? How do you make sure you have all the gas? A container on top? So what about the gas in the reaction flask, the volume of the reaction flask when it's full? It's not full. How do you account for that? What about the container on top? It would have to be evacuated, right? Otherwise there would be some air in there, and that would be contributing to the pressure. So that would kind of mess it up too. So these are like, I'm not trying to like tell you don't have good ideas. Like that is the obvious idea is to capture it in a flask, and there's reasons why that doesn't work. It doesn't work very well. So one way that you can capture gases is by bubbling them through a liquid and displacing the liquid. Probably makes the most sense to look at a picture of it. Oh, I didn't pull up my pictures yet. Let me grab those pictures here. Okay. Okay, so here's how you would do this. So here's the reaction. In this case, it's zinc reacting with HCl, forming hydrogen gas. You did this reaction last week. The zinc, the HCl bubbles. All the hydrogen that's being produced goes through this tube because there's a pressure created there. And what you do is you have like an inverted container that's filled with water. If that container is filled with water, then we know there's no gas in there. So we don't have to worry about like atmospheric gases influencing our results. Instead, as the hydrogen is produced, it displaces the water, and the water gets pushed down out the bottom part And so all of that volume in that container is due to the hydrogen that's been produced. And so that way we can measure how much volume has been displaced and know exactly the volume of the gas that's been produced. There's one problem with that. Does anybody see what it is? There's one thing that gets in the way of that nice, easy calculation.
Over water.
Yeah, what's wrong with what does the water do?
And more oxygen. I don't really know what it does.
It actually adds water is the problem. Water has a vapor pressure. Anybody know what vapor pressure means? A vapor pressure is the pressure created by the gas just above the surface. So, and we'll talk about what that means when we talk about solutions and boiling and stuff. But when you've got a sample of water, there's always some water vapor above the surface. As you increase the temperature, that amount of water vapor increases. And then at the boiling point, there's actually the same amount of water vapor pushing down on the surface as there is just atmospheric pressure. That's what we call boiling. So in other words, there's no more barrier for water to leave the solution. So any sample of water has some water vapor above it, which means that this nice little neat apparatus we have still has the issue of some water molecules in with our hydrogen. So we correct for that because we can measure and we can look up the vapor pressure of water, and we can simply subtract it. That's what's nice about this law of partial pressures. As long as we know the pressure of one gas, we can just subtract it and get the other one. So let's take a look at how we would do this question now with that new information. I'm going to move this over here. So it starts out normally. Hydrogen peroxide was catalytically decomposed, and this much gas was collected over water at 25 degrees C and 745 torr. What mass of oxygen was collected? So we're asked for mass. That means we're going to first solve for moles and then get mass. So it starts just like a regular ideal gas law type problem. We would say, let's do our conversions. So 25 degrees C is 298 K. 742 torr is 0.976 atmospheres. And we've got our volume. .0753 liters. So we just solve for moles. Let's see, there is a problem here. Yeah, let's not go through the whole equation. So it looks like a normal ideal gas law equation. We just solve for moles and then we solve for grams. The problem is, as we just talked about, there isn't just water in there. So if we solve, or just hydrogen in there. So if we solve for N, we'd actually be solving for moles of water and hydrogen. Since we know the pressure of water, we can actually subtract that out first. So we're going to say the total pressure is 742, but we don't want the total pressure. We just want the pressure of oxygen. So let's put that other equation on hold for a second. The pressure of oxygen is going to be the total pressure minus the vapor pressure of water. So minus the amount of pressure that water is contributing to. And so that's going to be 742 torr minus 24 torr, right, which is 718. And if we convert that to atmospheres, it's a little bit less. So we've just subtracted out the amount from water. Now we can solve for moles of just oxygen using the pressure for just oxygen. So that's going to be 0.945. The rest of it proceeds just like before. Point 00291 moles of oxygen. So if we convert that to grams by multiplying it by the molar mass 32, 0.0931. So that's B. Now, do you think that if we would have just used 742 torr, we would have gotten one of those answers? I think it's C, actually. If you would have used 742 torr or 0.976 atmospheres instead, if you would have not subtracted for the wave pressure of water, that answer still would have shown up, and so you would circle it and go on, but you'd be wrong. So the key you want to look for here is collected over water. If you see that collected over water, you know you need to subtract that partial pressure due to water vapor. And then you can proceed as usual. Now that said, you do actually have to be given that vapor. Like you can't just, you're not supposed to just know the vapor pressure of water. You would look it up in a table, or it would be given in the question like this. But that's how you would do that. Okay. Feel all right about that so far? Maybe. Let's kind of leave the math portion of this chapter and get into a little bit of the theory. So remember we talked about the difference between laws and theories. Anybody want to give us a refresher on that difference? Because it's an important one. What's the difference between laws and theories in science? We're going to see an example of that right now. Yeah.
A law is something that needs like further, it's like an idea, we need like some further testing, but it's like pretty good idea. But theory is one that's been tested over and over again and it works all the time.
Not quite.
Ah.
They actually speak to different things, yeah.
Oh, that is something that you see happening over and over.
Yeah, that's a better way to describe it. The law is something you see happening over and over again, but it doesn't explain anything. You're just describing what you see. And then the theory is what's going on kind of behind the scenes to explain that. So we have gas laws, right? Boyle's law, Charles' law. Why are those laws? What do they do? Let's take Boyle's law for an example. That's the pressure and volume one. So what does that say if we were to say that in like a sentence? Kind of like what we just did with those graphs. What's a sentence that describes Boyle's law? Pressure and volume. Yeah. Okay, so we can explain it like in a math way like that way. So another way of saying that is the product of pressure and volume is always constant. We could also talk about the changes. So we could say volume, as volume decreases, pressure increases, or as pressure increases, volume decreases, that kind of a thing. Those are laws because they kind of describe a thing that's happening, but they don't say why. And the reason this distinction is so important is because it comes up in things like, I mean, well, like it's important to know that distinction, but in terms of this class, you'll see this on exams. It'll say, what's the best explanation for why pressure or why volume decreases when pressure increases? And a lot of people will write because of Boyle's law. But that's a really not good answer because that doesn't explain anything. That's simply restating it. So if I say why does the volume go down, and you say, well, because pressure increase leads to a volume decrease, You're just saying the same thing that I just said in different words. So now we want to look at what's the theory. What's actually happening with the gas molecules that's causing these changes? So that when you're asked, why does this happen, you don't just restate, well, because of the equation, because that's not a reason. It's what's happening with the actual molecules that's causing that. So the theory that does this is called the kinetic molecular theory of gases. And a lot of it is stuff we've already been talking about, but there's a couple important points that we need to look at. All right, so we're going to write down kind of the major basic like assumptions or ideas, and then we'll look at how that explains everything. These things are all stuff we've already kind of talked about, but we'll put it officially here. The size of particles is negligibly, did I spell that right? Nope. Small. Okay, so that's saying that we don't have to worry about the size of the actual gas molecules. Now remember, these are assumptions for the theory, for things to work. They're not necessarily absolutely true. In this case, this is an example of that. So particles do absolutely have volume, and some are bigger than others. But compared to the space between them, that size is so small that we don't have to care about it. We can just ignore it. So that's what this is saying. That if you have a giant radon atom, or if you have a tiny hydrogen molecule, then we're going to say that those two things are basically the same size. That the difference between their sizes doesn't matter. So this also means that all of the volume is all due to the space between particles. So if we say we have this much volume, we're just talking about the space. So if we compress it, if we talk about pressure, we can say things like that we're decreasing the space between the molecules. And that's why you can compress a gas and not a liquid, because there is so much space compared to the size of the particles. Okay, second assumption is that the average kinetic energy of particles is proportional to the Kelvin temperature. Or temperature in kelvins is a better way to say that, I guess. So what does that tell us? Well, this tells us something about the motion of the particles. Does anybody remember from physics what's the equation for kinetic energy? Yeah, thanks. Kinetic energy is 1/2 mv squared, where m is mass and v is velocity. So this tells us that the temperature has something to do with the speed at which the molecules are traveling. So if we increase temperature, what are we doing to the speed of the particles? Yeah, they're going faster. That's what it means that it's proportional. If we increase temperature, the kinetic energy is going up. And assuming we have the same size particles, the velocity has to go up then. So we're saying that they're moving faster. Another way of thinking of using this idea is to think about sizes. Okay? So if you've got two samples of gas, helium and radon, so helium's super light, radon's super heavy comparatively. If they're both at the same temperature, which one is going faster? So if they're at the same temperature, the kinetic energy is the same. If one of them's lighter and one of them's heavier, which one's going faster? The lighter one's going faster because you got mv squared. So if the m goes down, the v has to go up to compensate. So lighter particles are going to travel faster than heavier particles at the same temperature. Okay. The third assumption is collisions are completely elastic. What does that mean? Physics folks, what? Yeah, they never lose energy. So when two things hit and they bounce off each other, there's a little bit of a transfer of energy there. Right? Like if a heavier thing hits a lighter thing, it transfers some energy, and then you can lose some energy due to friction, and like there's all that kind of stuff you can talk about in physics. Well, we're going to assume in a gas that the collisions are completely elastic, which means no energy changes when they're hitting each other. They don't lose any energy. Everything just like it bounces off like this, and it goes exactly the same way with the same type of velocity. Same thing with the walls. We already talked about this. Collisions with walls create our pressure. So this answers the question I kind of brushed over. I think Kyle said at the beginning of class. Maybe it was somebody else. When I said, like, when we talk about partial pressures, do we have to worry about the gases interacting in some way? And somebody said, well, yeah, we do. Was that you? I don't remember.
That doesn't mean I think someone else.
Okay, so somebody said, like, yeah, we have to worry about the gases. This is why we don't. Because when gas molecules hit each other, they just bounce off and nothing's changing. So nothing really happens. And because of that, we don't have to do any weird stuff to compensate for that in our calculations. We can just say the only pressure is created by the gases hitting the walls. And we don't have to worry about them hitting each other. All right, so those are our assumptions. So let's talk about how they explain something like Boyle's law. So we know Boyle's law is pressure times volume equals constant. Okay. As pressure goes up, volume goes down. As volume goes up, pressure goes down. Whatever. So now let's talk about why. How does the theory explain that? And to do that, we're going to think about collisions. If the gas particles, if we want to say what happens when we increase pressure, how do we word that in terms of collisions? What does increasing pressure mean when we talk about gas molecules colliding with the walls? Right. So when we say increase pressure, what we're really saying is more collisions. So there's three ways we could get more collisions. Think about your container. You've got the gas is hitting the walls at a particular rate, and you want more collisions. What are the three ways you can get more collisions? So one way would be increasing the temperature. The gas molecules go faster, and therefore they have more collisions. Does that explain Boyle's law? No, not and because why? We should say that because there's another part here really. The temperature is constant. Temperature changes, then we've got a whole new situation we have to deal with. But so when temperature is constant. So if we say we want more collisions, one way we can do that is to increase temperature, but in this situation, temperature is staying the same. So what's another way we can increase pressure?
Decrease volume.
Yeah, we can decrease volume. So to explain Boyle's law, we would say, actually it kind of makes sense to think about it more the other way, to say if the volume goes down, if we decrease the size of the container, there's going to be the same amount of gas in a smaller space, so they're going to hit the walls a lot more, and that's going to increase our pressure. So that's kind of the explanation. That's the theory behind it. If those assumptions are true that we just talked about, then we can say that we can explain this based on these collisions. What's the third way of increasing collisions, by the way? Think about the different quantities in the ideal gas law. You can change the temperature, you can change the size of the container.
Increasing the number of moles.
Yeah, you could increase the number of moles. If you put more gas in, what would happen to the collisions? You'd have more, right? Because there'd be more in there hitting the walls. Yeah. So we can use that same type of language to explain all the different laws that we talked about. Even like what we did today, Dalton's law, the partial pressures thing. We can say, well, the pressure is caused by the collisions. The collisions between gas molecules are perfectly elastic. And so partial pressures must be additive because the different gases don't depend on each other for how they hit the walls. That doesn't affect anything. All right, we're almost done talking about gases. Let's stop here and take a break. We will kind of come back and talk about some other consequences of the kinetic molecular theory, and then we'll talk about lab. We'll go through the limiting reactant calculations and getting ready for tomorrow's lab. So I'll see you in about 15 minutes. Try to remember the time this time.
Did you say 10 minutes?
I said 15.
All right.
You can come back in All right, I just want to take a look at a couple graphs that describe some factors that we've been talking about, but kind of make it a little bit more clear. So we said, what do we say about velocity versus mass? At the same temperature, which things go faster, heavier things or lighter things? Lighter things. So that, based on the kinetic energy equation. That's true, but it's a little bit more complicated than that. The better way to say it is, on average, lighter things travel faster than heavier ones. And that's what this graph is showing. So this one shows us molecular velocity on the x-axis. And then the y-axis is kind of like a histogram. It's the relative number of molecules with that velocity. So if you look at hydrogen, for instance, the long green one that kind of stretches way out, the average is kind of in the middle there. But there are hydrogen molecules that are traveling really slowly. And there are hydrogen molecules that are traveling much, much faster. What happens as the gas gets heavier, as the molar mass increases? What happens? The velocity decreases, but careful, the average velocity decreases, right? Like there's still a range, but the average decreases, and also the range decreases. So if you look at oxygen, the heaviest one in this graph, O2, has the skinniest curve, which means that there's the smallest range of different velocities. So this tells us that we need something called an average, and the average that we use for this, because of the shape of this curve, we don't use a direct, like regular old kind of average. We use an average that's called the root mean square velocity. And it's just an equation. You'll see in the homework. You don't need to memorize this equation for the exam or quiz or anything. I'll give you the equation if you need it. But this is this average. It's a type of average velocity. We use these in electronics also. You can talk about the RMS voltage and things like that. It's what it sounds like. You take the square root of the mean of the squares, and it's just another way of doing an average. But the way we do it for gases is we put it in terms of the temperature, the Kelvin temperature, and the molar mass. So the heavier gas is going to have the lower average velocity. And if you want to go through the derivation and stuff that's in the book, it's not that big of a deal, but you can get there. Basically, you take the kinetic energy equation and you substitute in temperature and you substitute in molar mass for mass, and you got to kind of go for there, and then you do the averages. But the point of all of this is, the important thing to remember is that there's a range of velocities of gas particles always, and the temperature is proportional to the average. So when we say that one of them is slower than the other, we're not talking about individual particles. We're talking about, on average, the lighter one is going to be moving faster than the slower one at the same temperature. Okay. Changing the temperature also changes this velocity distribution. So grab the graph of that one. That's this one here. So this is just one gas. This is just nitrogen. But we see kind of the same thing happening and the same effect. As the temperature increases, the range increases and the average increases. So when we say that gases move faster at high temperatures, more of the gases are moving, more of the molecules are moving faster. On average, they're moving faster. But even at 2000 K here, compared to 0 degrees C, compared to standard temperature, if we compare those two, there's still, let's say about this much of the gases in that really, really hot sample that are moving the same speed as the average and below of the polar cycle. So there's still going to be this range of gases, this range of motion over time. Okay. A couple other little things that we should know about. And miscellaneous topics at the end of the chapter here. Standard temperature and pressure, or STP, is 1 atmosphere and 273 K, or 0 degrees C. This is a definition. It's just, we call that standard temperature and pressure. 1 atmosphere, 273 K. Exact numbers. We know that's also 760 millimeters of mercury per torr. So what's the consequence of that? Well, the consequence is we can have something called a molar volume. If we solve the ideal gas law, we put in standard numbers. So standard pressure is going to be 1 atmosphere. Standard temperature is going to be 273 K. We can substitute in 1 mole and solve for volume. So we can always know the volume of 1 mole of gas. And if we solve that, we get 22.41 liters. And this is known as molar volume at STP. So if a question says, like you'll see in the homework, at standard temperature and pressure, at STP, you have X amount of whatever, you can avoid an ideal gas law calculation by just knowing that every mole of a gas at STP is going to take up that much space. So if you have half a mole of oxygen at STP, you could just cut that number in half. You don't have to like solve the whole equation to get the volume. That's helpful in comparing gases as well. So like another thing we're going to look at here, we've always talked about ideal gas, ideal gas, ideal gas. We have all these assumptions, they don't take up space, blah, blah, blah. But there's actually real gases in the real world, and they don't necessarily behave like ideal gases. We spend a lot of time on the ideal gas law because it's a pretty good approximation. And in most situations, it works. But in a lot of situations, or in some situations, it doesn't. So we need to talk about what those situations are and what affects those things. So there's 2 things that affect that. I'm not going to put this graph in the notes because it's kind of dumb, but we can look at it. Okay, I guess that's the best we can do. So if you actually look at how much volume gas takes up at standard temperature and pressure, you see a slight variation. Sometimes a significant variation. So an ideal gas is 22.41 liters at STP. We just talked about that. But these are all actual samples of real gases. If you measure them, you get varying numbers around 22.41. So this is telling us that a gas like helium is pretty much behaving ideally, but a gas like chlorine is really not. It's actually pretty far off. So something's going on that is violating our assumptions for what ideal gases do, and we have to figure out what that is. So there's two factors that do that. And we can kind of figure them out based on how we knew some of those assumptions were wrong. So the first one is particle volume. What was our assumption that had to do with particle volume?
It's negligible.
That it's negligible, that we don't have to care about the size of the individual molecules. But in some cases we do. So what are some situations that you think we might have to care about particle volume? When would it start to become important how big the particles themselves are, rather than just the spaces between them?
They bump into each other.
Yeah, well, they're always bumping into each other.
Oh, yeah.
But what kind of situation? Yeah, so you're on the right track, yeah. If we're talking about, so like, more of them, maybe?
Yeah.
Sure, okay. We want to add to that? Yeah, it's when they get really close together. So if you have if your particles are really far apart, which they usually are, then the sizes of the individual particles don't matter. But once they start getting closer and closer together, then their actual sizes end up mattering. So when does that happen? Yeah, when we get really, really high pressures, the particles end up really close together. So here's a graph that kind of shows that. We'll go through it and see how this works. Where is it? Yeah. So look what's happening on this graph down on the right side. So at the left is like normal pressure. And look at these numbers too. 1 atmosphere is way down here. So we're mostly talking about super, super, super high pressures. As pressure gets really, really high, the actual real gas, argon, has a slightly lower or slightly higher volume than what's predicted by the ideal gas law. And so what's happening there is the actual space that the molecules are taking up isn't being accounted for in the ideal gas law. And so the volume is a little bit higher than you would think because the individual particles are contributing to it, even though we're not taking them into account. At low pressures, this doesn't matter. But at high pressures, the volume is higher because of the particle size, because of the individual particles are actually taking up space. So that's number one. Number two, is intermolecular forces. Another assumption that we made was that collisions are purely elastic and that molecules don't attract each other or repel each other. They just kind of are around. But we know that's not actually real because we know real molecules actually attract each other. They all do. So we have liquids, solids, all molecules have some attractive forces. So at really, really low temperatures, this becomes a problem. So let's look at the other graph here so we can see what that looks like. So when we cool a sample down, the pressure is lower than predicted because the gases are kind of attracting each other. So they're not colliding with the walls as much as we expect because they're kind of being pulled together and held together by their own forces. This isn't an issue at high temperature because the high temperatures are breaking all those intermolecular forces. There's plenty of energy to do whatever. But at low temperatures, the gases are attracting each other, and so the pressure is lower than expected because they're not hitting the walls as much. They're kind of attracting each other more. So we could say something like attractive forces are preventing wall collisions. that's why the behavior is different from ideal. So you've got two factors that are affecting this. One is the particle size affecting the volume, and the other is the forces affecting the pressure. If you think about what's happening, hopefully you can help to keep those straight. The volume issue is the space that the molecules are taking up. So since they're taking up space, the volume is bigger than expected. And then the other one is the attractive forces making the pressure smaller than expected because of the lack of collisions. There are these factors to actually calculate this. We'll take a look. Here, where can I put it here? We'll just put it down here. Actually, is there a picture of it? This will be easier. No. Okay. So the correction for particle volume is that instead of V in the ideal gas law, you use this factor V minus NB. And that B is a it's called a van der Waals factor. And you just have to look that up in a table. So it's not really, there's nothing I can tell you about how to figure that out. It has to be measured, and then there's a table that you can look it up. So the only reason I'm really putting this on there is because it will come up in the homework. If it came up on an exam or something, I would give you those numbers. There's our A and B factor. I don't care so much that you can apply these factors and do this calculation because that's just plugging numbers into an equation. But you should be able to explain what the effects are. So why do some gases deviate from ideality, and how do they deviate based on all those things we just talked about? If you want to actually calculate it, you can just plug those numbers in. You can look up A's and B's on a table and plug the numbers in. So if you put this all together, it can actually make a pretty big difference depending on what kind of a gas you're dealing with. So this is the moles of gas at different temperatures, right? The ratio between, like 1 mole of gas, the ratio between PV and RT. And so a perfectly ideal gas, that would be perfectly constant as temperature. Is that temperature or pressure? That's pressure. Pressure. So as pressure increases, the moles essentially should go linearly. But with other gases, it kind of does all weird stuff depending on how those things deviate, depending on those A and B factors. So again, there's some effects at higher pressures and then some at lower temperatures.
Xenon is weird.
What?
Xenon is weird.
Yeah. So I mean, water's pretty weird too.
Why is the environment weird?
Right. So ideal gas should always stay at 1 mole, or should always, that ratio should always be at 1, and these other ones, they're not. So depending on pressure. So again, you don't need to be able to calculate those, but there is one more thing in the book called effusion. Again, it's something that could come up in your homework. If it's on an exam, you'll be given an equation, so you don't need to memorize anything. But effusion describes gases going through a very small hole. So what do you think goes through a very small hole more quickly? Larger particles or smaller particles? Smaller particles. Yeah. So that's the whole point of this, is that smaller particles effuse more quickly. And so you can actually calculate an effusion rate, and it's a way of identifying a gas or determining what you have. And it looks like this. Again, this isn't something you need to have memorized. But the ratio of the rates of two gases, of the effusions of two gases, so you got a light gas and a heavy gas, the ratio by which they would go through this hole is proportional to the square root of the opposite of the ratio of their molar masses. That's what those M's are. So again, this is just a plug in the equation kind of thing. If you've got two gases and you want to know the effusion rates, or you want to know the ratio of the effusion rates, you plug in their molar masses and it'll tell you how fast one effuses compared to the other. You don't need to memorize that equation. All right, that's all the stuff. Let's look at some problems and practice some of these. Some of these later ones. So let's flip to the last page. I think this is the last page, right? We've got two of these kind of qualitative idea questions for the stuff we've just been talking about, and then two of the more typical calculation type questions. So in your groups or on your own, however you want to do that, let's work through these four questions, and then we'll talk about them, and then we'll move on and look at the lab. This will be a good way to sum up what we've been doing with the essays. Yeah. So that's what, yeah, that's what we just talked about. The root mean squared molecular speed is a type of an average. So you can replace that with average and see if you can answer it without actually doing a calculation. That one should not require a calculation. You should be able to look at those, at least not a complicated calculation. You should be able to look at those molecules and figure out which one is going to have the greatest molecular speed or the greatest average speed at
Yeah,
a
I left
given
like a minute while
temperature.
you were talking about this. I didn't get that.
Okay, so talk to people around you. Let me know if you're stuck. No. Yes. Big and the small. Those are usually quite below. Yes.
I said it's. No, just. Oh, no. I mean. Oh, yeah, it's looking for some. Oh.
Do this a little bit backwards, come backwards, I think what I needed. So I get clarity. Just look right. 30. I didn't use. I don't know how to go.
Well, because you have to first check about.
That's fair. You get two reactions, both quantities are given. Whenever both quantities are given, that's a good bet. So that might have given you. Yeah, so you have to check. If you're stuck on that third one, think about the quantities that are given. You've got aluminum, a certain amount of aluminum, and a certain amount of HCl. So you're going to want to convert those to moles and then compare and do the limiting reactant type stuff for that one. The last one, there's only one reactant, so there could be a limiting reactant there. Also for 84, if you get toward the end, you can use the ideal gas law, but there's a shortcut. If you know the volume at STP, you know that number 22.4, you can put that in there also.
So Joe?
Yeah.
Limiting reactant is the one where, like, say, if you were to use all of it, you would have some, you would only use part of the second one, correct?
Right.
Alright, next year. Yeah. So I'll check some of this, right?
Yeah. I don't know if you need.
Well, no, it's more like,
Okay.
it's more of a general thing of like, so I like 6 more, I feel like, and you might have 26 more, you know.
Right. Yeah.
Making sure tonight, thanks. There.
So what do you call it?
Like, after this is what's like, this is right? So no part.
Yeah.
And that was it in there, it's just, it's 50 grams, but if I did change it to beer, the point is, it's 21. Which makes sense. Yeah. Yes.
All right, let's take a look at these. Keep working if you're still working. I know a few of you are still calculating. The first couple. So how do we do number 62 without a calculation? Or at least without a big calculation? What is the molecular speed proportional to, assuming the temperature stays the same? Mass, right? So that's what that question is asking. It's not asking you to do a calculation or a bunch of calculations for root mean squared molecular speed. It's just saying, okay, which one has the highest average speed, knowing that the speed is proportional to the mass. So that way we can just look at the masses and go from there. So which one of those has the smallest mass? Hydrogen, H2. So that's going to be the fastest, right? Whatever's the smallest is going to be moving the fastest on average at that temperature. So that would be C. What about 66? So now we're talking about those issues where we deviate from ideality. When do we have the most like an ideal gas? So you have to think about the two effects. The particle size effects, that happens when? At high-low temperature or high-low pressure, when it becomes an issue that particles actually have size. Where is that an issue? Yeah, particles, right. So that's for both of them. For particle size specifically, we're talking about the pressure, because as the pressure gets high, the particles get really close together, so their actual size matters more. And then the other effect is the attractiveness effect. As the particles go to low temperature, the fact that they attract each other becomes more important because they decrease the effective pressure there. So at low temperature and high pressure, that's where you have, that's where you have the biggest problems. So at high temperature and low pressure, we got to read the question carefully. That's where it's going to be most like an ideal gas. All right, now let's take a look at these calculations. So in this calculation, we want to figure out what's the limiting reactant, because we're given quantities of two reactants. We're given aluminum and HCl. And I know different people have different ways of doing this, so however you do your limiting reactant stuff, as long as it works, is great. The way I do it is I convert both to moles and then look at the mole ratio. So 10 grams of aluminum in moles. Oh, I got a lot of stuff open. 10 grams of aluminum in moles, 27 grams per mole. So that's 10 divided by 27. .370 moles. Now the HCl, I've got 100 milliliters of 6 molar hydrochloric acid. So that's 0.1 liters, and 6 molar tells us it's 6 moles per liter. So 6 moles per liter times 0.1 liter is 0.6 moles. In this particular question, I can look at those two and see, probably without doing a calculation, because I can look at the equation and see that aluminum has to be in a 1:3 ratio with HCl. So it has to be 3 times as many moles as HCl. There's not, right? There's 0.370 moles of aluminum and 0.6 of HCl, which means the HCl is limiting. Because in order to have enough HCl to react with all that aluminum, we would need 3 times 0.37, which is way more than 0.6. So that tells us the HCl is limiting. Once we know that that one's limiting, then we can do the rest of the calculation just like a regular stoichiometry thing. We're going to solve for hydrogen, and then I'll show you how we fit that molar volume in there to make it even easier. So we go 0.600 moles of HCl. And then the equation gives us, from moles of HCl to moles of H2, and that tells us it's 6 to 3. So now we've got moles of hydrogen. So we could take the moles of hydrogen and plug it into the ideal gas law and solve for volume. But because it's an STP, we can simply use that as a factor and say that there's 22.4 liters of hydrogen in every mole. That only works at standard temperature and pressure, but as long as we're at standard temperature and pressure, we can use that and save ourselves a little time. So 0.6 times 3 divided by 6 times 22.4. 6.72 liters of hydrogen. All right. So the first part of that question is just standard stoichiometry stuff from chapter 4. The last part is we use that molar volume to figure out the amount of hydrogen. In the next question, we can't do that because we're not at standard temperature and pressure anymore. So we are going to have to use the ideal gas law here. 10 grams of glucose, we'll convert that to moles. Did anybody come up with a molar mass for glucose? Did I get that far? 180? So this tells us we're going to make 0.111 moles of CO2. We want volume. So that's 0.111 moles. Temperature is 25 C, which is 298 K. And then our pressure is 745, which is 0.980 atmospheres. So we've got 2.77 liters of CO2. Is that what you got? Similar to that? Okay. So that's how you combine some of these Gauss calculations with the stoichiometry we've done before. That's going to be the major part of this chapter. Make sure you can do those types of calculations, that you can fit them in with limiting reactants, with all the other stuff we've already done. And then some of the descriptive stuff. So like, just quickly, let's take a look at this one. This is how you might have a question on effusion or effusion rate. Which of those is going to get through a little hole the fastest? Which one? Close. Yeah, it's going to be ammonia. So I think you're on the right track. It's going to be the lightest one. Ammonia is NH3. Nitrogen is N2. So NH3 is lighter than N2. N2 would be 28, and H3 would be 17. So ammonia should fuse the fastest. Okay. There's some more practice here if you want to do it. Some of the stuff we did before with density and all that. For the last 40 minutes of class or so, let's take a look at the lab and make sure we know what we're doing with that. So once again, there's an updated procedure here. This happened with another one too, because we had it more of like a report format in the semester. I think that for the purposes of this class and with all the other stuff we've got going on, it makes more sense to not do this and focus on just this part. So you don't have to necessarily do it on this form if you've already done it in your notebook or on paper or whatever. But these are going to be the questions that that are important. So let's talk a little bit about how you do that if you haven't figured that out yet. I'm not going to go through and do your calculations for you, but it can be a little bit confusing. So we have to think about what we did in this reaction. So first of all, the equation isn't given here, so you have to come up with a balanced equation. I think you can probably do that. But what is the precipitate that's formed? What is the identity of the precipitate in this reaction? Probably even says, isn't it? So you got sodium phosphate and zinc sulfate.
So zinc phosphate.
So zinc phosphate, because we know sodium salts are always soluble. So sodium phosphate and zinc sulfate, that means the zinc phosphate is going to be the precipitate. And so you took that out at the end and you weighed it, and you know the mass of the product. So let's say you started with, how much did it say? So let's see, about 2 grams. So let's say you started with 2.000 grams of the mixture. And let's say you had a 50-50 mixture. Remember, you don't know what your mixture is, but we're just, for an example, let's say that's what we got. So that means that we had 1.00 gram of one of them and 1.000 gram of the other one. Those are the two reactants. All right. So you put those together, you reacted them, and you made some amount of precipitate, zinc phosphate, and that's what you measured. Now think about that as if it were like a homework problem. You know how much precipitate you formed, so you should be able to work backwards and figure out how much of each reactant you had. The tricky thing about this is that they weren't in a stoichiometric mixture. So let's solve this through, just as an example, with this one right here in the forward direction, and then you can figure out how to do it in the backward direction for your report. So the equation looks like this. Okay. I mean, you can figure out the states there. That's the balanced equation. So we could work this through like a limiting reactant problem. You'd convert that 1 gram to moles, convert the other 1 gram to moles. Let's use our internet helper and figure out what that would be. Okay, so if we had 1 gram, that would be 6.1 millimoles. And if we also had a gram of zinc sulfate, it would be 6.2 millimoles. You should use more significant figures, of course, when you do your actual calculations. But just as an example, so which of those two is the limiting reactant here in our example?
No, I think we need to figure it out.
No, it should be the other one, right? Because we've got about the same number of moles of each, but you're supposed to have 2 of one and 3 of the other. So the one that we have less of is, all right, let's just do the calculation so it's clear. 6.1 millimoles of Na3 PO4 times 2 of those okay. So that tells us that if we have 6.1 millimoles of sodium phosphate, we need 9.15 millimoles of zinc sulfate. We don't have that. We only have 6. So that means we have less of the ZnSO4 than we need. And so that one is limiting. See how that works? When you have less of what you need, that's the limiting one. So that means that the most precipitate that we can form is based on the zinc sulfate, which is 6.2 millimoles, since that's 1:1. So let's say this is what happened. You got perfect yields, whatever. You got 6.2 millimoles of sodium sulfate. Or whoops. Sorry, that's not our precipitate. This is the precipitate. So we got to divide that by 3. So we got 2.1 millimoles of precipitate. .811 grams. Okay. So now we've got example calculations here. Remember, this is not the procedure you're going to use specifically for the lab because we're going backwards. I just wanted to have some numbers so we can talk through what you're going to do going backwards. All right, so what this looks like to you is you started with 2 grams of mixture, you did your reaction, you filtered it off, you let it dry, and then at the end, you came up with 0.811 grams of product. That's the white powder. So you have to work backwards to figure out what you started with. So let's imagine that this is what happened. And let's work backwards the other way. So you go through and you start doing your stoichiometry stuff. You convert 0.811 grams to millimoles or moles, whatever. That's zinc phosphate. And then you want to do your mole conversion or your mole ratio to figure out the reactants. But there's a problem. Because if you do that for each of those, you're going to get the right answer for one of them, and you're going to get the wrong answer for the other. In other words, if we go through and do our stoichiometry calculations using 2.1 millimoles for this, you're going to correctly calculate 6.2 millimoles of this, but you're not going to get this one right. Why not? Yeah, because you don't know how much excess there was. If you've got the product, you don't know how much excess of the other reactant there was. All you've got is the product. So how do you figure that out? That's kind of the tricky calculation in this lab. How do you figure out which one you're supposed to calculate if you don't know which one was limiting? Or do you know which one was limiting?
You know which one's limiting from when we added.
Right, right. So that's really the key to this lab then. The part B, you tested for the limiting reactant. So you know which one's limiting, and that's the one you can solve for. All right, so let's say we did this. Let's do an example calculation. So let's say the test showed that the zinc sulfate was limiting, which is the situation here. So that means that we can calculate back both of those, and we calculate back that we should get, so we got 2.1 millimoles of precipitate. And that's going to give us Sorry, drawing the wrong thing here. So this should give us the correct number if we do the 3:1 ratio. So it'll be close anyway. And if we do the same thing for the other one, oops. We got 4.2 millimoles. So if we convert those to grams, that's how much was actually used in the reaction. Because we know that this one was limiting, we know all the excess amount that we had was due to this one. So let's convert those back to grams. So this is about, well, we've lost all our precision here, but this is about 1 gram. This is about 0.69 grams. So that, since we started with 2 grams, that tells us that extra 0.3 grams must have been the sodium phosphate. If we didn't know which one was limiting, we wouldn't know, is that extra 0.3 grams zinc sulfate or is the extra 0.3 grams sodium phosphate? So now we can say, okay, we know that the bottom one was limiting. We got 1 gram of each. So therefore we have a 50% mass ratio. I think that's what's asked for here, right? The percent by mass of this is 50-50. So 50% zinc sulfates, 50% sodium phosphate. That's what you're ultimately trying to calculate here. What was the mass ratio, or what were the masses of each of those in your initial mixture? Right? So you got to use the information from both parts of the lab to get that. Yeah?
Can you say that just this sheet is what we turn
We'll still turn in your data so I can like look at it and stuff, but this is what I'll be like grading as a report. You don't have to answer all those other questions that are in the report.
So for question 5 on 61 is to explain like the process, how we got there, just
Yes. So basically, you don't have to explain it. Just show the calculations and then like which one was which. The this part you have to explain.
Yeah.
How you figured out which one was limiting and which one was excess.
But like question 4 then.
Yeah.
Like, how would we word it differently than saying
It's the same. I mean, 3 and 4 are kind of the same question. Yeah. You could talk about it. Yeah, they're the same question. Yeah. That's probably why I revised it for the other year, but I need to revise this form too. All right, good so far? Okay, let's talk about tomorrow's lab then. The other lab, by the way, is also due tomorrow, the chemical reactions. That's more straightforward. You just write the reactions and explain your lab challenges and how you learned it, that kind of thing. Let's look at tomorrow's lab. Tomorrow's lab is flame tests. Whoops, where's labs? I think. Is that right? Okay. I didn't check the schedule. I should have checked the schedules. The pre-lab activity, I don't think we're going to do. Yeah. So skip the pre-lab activity for tomorrow because we'll do it together, and you have enough to do with the other lab reports anyway. So yeah, just do that. And then we're going to talk about this stuff on Thursday. This is chapter 7. So we'll get to this stuff on Thursday, and then you'll be able to do this. And we'll just make this part of the report because it works nicely with the report. Tomorrow's actual lab, like the stuff that you do in lab, is really, really short. So after lab, we'll come in and we'll talk a little bit about what this stuff means and how we figure that out. All right, so we got about 25 minutes. What do you want to do? Yeah.
Do we have quiz or quiz for chapter 4 tomorrow?
No, the quiz will be on Thursday. Yeah, on chapter 5. Chapter 5, the gases. Well, no, did we say, what did we say? I can't remember now. Yeah, I think we said chapter 5. Is that, yeah, because then we'll do a quiz on Monday on chapter. Yeah, let's switch that. Let's do chapter 4 quiz on Thursday, even though we had that on the exam. And then we'll do chapter 5 and 7 kind of together on next week quiz on Monday. Is that okay? Does that mess anybody up? Because we haven't done the chapter 5 homework yet. There's only 2 days. It's not enough time to get ready for a quiz. Okay, so do you want to do more practice? All right, let's look at some other of these gas calculations. So now we're on the second page, third page. Let's work through some of those. So the first one is kind of a combined gas law problem. So we change some of the things and then you figure out the other thing. So it takes this kind of a form. That's called the combined gas law because it combines all 3 of those relationships: pressure, volume, and temperature, and pressure and temperature. So if you've got something at one temperature and pressure and it occupies the volume of the other, and then you change the volume, keep the temperature the same. Oh wait, temperature's the same, so we don't have to do that. I'm sorry. This is easier than it looks. So this is just a Boyle's law because it's only about volume. It looked to me like temperature changed, but temperature does not change. So that's easy enough, right? You change the volume and you solve for the new pressure. Do you have to convert units here to atmospheres from torr? You don't, because we're not using the gas constant. And so as long as we want our answer in torr, we can just leave everything in torr and solve it directly. So that would be 248 times 275 divided by 321. Our answer should be A, 212 torr. So the second one's interesting because remember we used that kind of revised version of the ideal gas law that had density and molar mass in it. So let's say you get to your exam or your quiz, you don't remember that other formula because it's really not a formula that you need to memorize. So how could you solve this if you didn't remember that different version of the ideal gas law? This is all you need. How could you do this just with like regular ideal gas law stuff if you didn't remember that other one? But yeah, you use the regular ideal gas law, you solve for volume. So and there's actually even an easier way to do it. We'll talk about it in a second. So you could solve for volume, but how would you get grams? How would you get n, number of moles? It's not given in the question. How do you do that? How can, if you get a situation like this, so you start solving this thing and you're like, oh, I need moles, but moles isn't given. Why isn't it given? What do you need to do? But you just pick. You pick whatever you want. It doesn't matter. We're talking about a ratio between a mass and a volume. So you pick whatever moles you want, you solve for volume, and then you divide them. And it doesn't matter what you pick, but what's a nice number that we might pick? 1, maybe? Sound good? 1 mole? So do we even need to solve this problem for 1 mole? To solve for V? Or do we just know that number? Maybe we don't remember because it's been a long day. Yeah. Yeah, so it ends up being, if n equals 1 mole, and we're at STP, then V has to be 22.4 liters, right? That's the molar volume. So if we assume that there's 1 mole, we can assume that the volume is 22.41 liters. So our only job then here is to figure out the density. Density is grams divided by liters. We determine that we have 1 mole, which is going to take up this much room. How much is 1 mole going to weigh? Can we figure that out? Because we want grams, not moles. I see some people looking at the periodic table. That's good. We look over at argon, 39.9 grams per mole. So again, if we're assuming 1 mole, that makes everything a whole lot easier. So our density is going to be 1.78 grams per liter, which is D. Now we could have picked a different number. We could have picked half a mole or 6 moles, but then we would have had to solve for volume, solve for grams, divide them, and we would have gotten the same answer. All right, this next one. What's special about this next one? Hydrogen peroxide. Wait, didn't we just do this one? We did that one before. Let's skip that one. But that was a special thing. It was about collecting over water. Let's do this one, 54, since that one's a little bit different from what we've done so far. Hydrochloric acid prepared by bubbling hydrogen chloride gas through water. What is the concentration of a solution prepared by dissolving all this stuff in some water? What are we going to do here?
Did you also have to subtract things because it's like through water?
It's a little bit different because we're not measuring pressure here, or we're not measuring a quantity of gas. We're saying that we're putting the gas into the water, like dissolving it in water. And so in this case, no. And the other clue here is there's no like pressure of water vapor given. Yeah. But we do need, so what quantity of HCl do we need ultimately to be able to figure out the molarity? What quantities do you need to calculate molarity of a solution? You need 2 things and you divide them. What are they? Liters is 1. And what goes on top? Moles, yeah. So molarity is moles per liter. So we need moles and we've got liters. we've got liters, so we need to know moles of HCl gas, and then we'll have our concentration. So how are we going to figure out moles of HCl gas? What kind of equation can we use here? Yeah, we're going to use the ideal gas law because we've got a volume, we've got a temperature, and we've got a pressure, so we can calculate moles after we do those conversions. So pressure 89.6 kilopascals divided by 101 is 0.887 atmospheres. Our volume is 225 liters. Our R is still 0.0821. And our temperature is 37 plus 273, which is 310. No, yeah. Oops, there. So we got 7.84 moles HCl. We divide that by our volume, so 7.84 moles divided by 5.25 liters is about 1.5 molar, 1.49 molar. So we had to remember that molarity is moles divided by liters to get that concentration. All right, I guess let's stop there. We've got about 10 minutes left. So if you have questions about mastering chemistry or other things, I'll be here if you want to, if you have issues with your lab or anything, any last minute questions. Otherwise, I'll see you for lab tomorrow. Don't forget, just skip the pre-lab tomorrow. Just make sure you work on those 2 reports.
I have a question about this.
Yeah.